In this video, we're going to talk about resonance structures and how to use resonance structures in Lewis dots. So resonance structures are going to be specifically areas where you have multiple Lewis dot structures for one, because there's usually going to be a delocalized electron that's going to be flowing around a Lewis dot structure. The second thing I also want to mention is going to be this idea called formal charges. It's usually to evaluate non-equivalent Lewis dot structures. And so when you're talking about non-equivalent Lewis dot structures, you want to be able to take a look at each atom to try to achieve a formal charge as close to zero as possible. And the way you do that is, if you have two structures that you want to figure out which is the correct one, what you want to do is make sure that any negative formal charge are expected to reside on the most electronegative element. So for example, if I take a look at fluorine and oxygen, if I can't get to zero, what I want to do is make sure that that Lewis dot structure reflects a formal charge that's going to apply to the most electronegative. And that kind of makes sense, right? Because that highly electronegative element is going to pull on those electrons more than others. Very similar to kind of like a polar bond, you want to say. Now, the way you do this is for formal charges is that you're going to take the number of valence electrons minus the valence electrons on the neutral atom minus the number of valence electrons assigned to the atom in the molecule. And so if you end up getting a positive number or a negative number, it usually means that you have more valence electrons on the free nuclear atom, or you have more on the actual atom itself. A couple of assumptions you have to make for formal charges are two things. The first one is that lone pair electrons belong entirely to the atom in question. So whatever atom you're trying to take a look at, those lone pairs belong to that one. And the second thing has to do with shared electrons are divided equally between the two sharing atoms. All right, so let's get started and do some practice in regards to a formal charge. So to calculate formal charges, take the sum of the lone pairs and 1/2 of the shared electrons. So we're going to go ahead and take a look at adding all the lone pairs plus 1/2 of those, and you're going to subtract them by the number of assigned electrons from the number of valence electrons on the free neutral atom. All right, so I know it seems a little bit convoluted, but once you see the example, you'll get to see what it looks like. All right, so the first thing is we want to take a look at PCl3O, and we're trying to assign the formal charge for each one on each of the atoms. So if you take a look at phosphorus versus chlorine and oxygen, we automatically identify chlorine as the most electronegative element. So if we do find a formal charge, most likely chlorine is going to be a negative, but we want to get down to zero as close as possible. All right, so the first thing is we're going to take at phosphorus. It's going to have a +1 charge, and the reason why is that it's going to have 5 electrons coming in, and it's actually sharing 4 electrons, one with chlorine, one with chlorine, one with chlorine, and one with oxygen. If you subtract 5 minus 4, you're going to get a +1 charge for phosphorus. For oxygen, you're just coming in with 6, but then oxygen here is actually going to subtract it by 7 because it's actually sharing 7 electrons. So 2, 4, 6, and it's sharing one with phosphorus, making the 7. So oxygen in this case has a formal charge of -1. And the chlorines are going to be 0. And the reason why is because if you take a look at chlorine, it's coming with 7 valence electrons, and it actually has 7 electrons that it's sharing. So 2, 4, 6, and then 1/2 for every line. That gives you a 0. So the answer here would be +1, -1, and 0. Now we take a look at this, we ask ourselves the question is, should oxygen have more than chlorine? And actually, I believe oxygen may have more electronegativity than chlorine. Apologize for that. I think earlier I had mentioned the other way. So this kind of checks out, and this gives us the actual formal charges for those. So the rules for governing formal charges is the sum of the formal charges of all atoms in a given molecule or ion must equal the overcharge on that species. So if I go ahead and go back to this example, if I add this up, it should have a 0 charge. So if I add +1, -1, and 0, that ends up being a neutral atom. And the answer is that it actually checks out. So if non-equivalent Lewis dot structures exist for a species, those with the formal charges closest to 0 and with any negative formal charges on the most electronegative are considered to be best describe the bonding in a molecule or ion. So here's a classic example of something that you can actually draw this Lewis structure in two ways, and it would still satisfy the octet, But the problem is that when you draw these out, you're wondering which one to do. So let's take a look at this example right here for carbon dioxide. Carbon dioxide, if you notice carefully, has 2, 4, 6, 8, 2, 4, 6, 8, and then it has 2, 4, 6, 8. But one of these is incorrect and one of those is correct. And so if we take a look at this one, carbon has a charge here of 0, because if you take a look at carbon, carbon comes in with 4 electrons and it's sharing 4. So carbon here has a 0 charge. Now oxygen comes in with 6, minus 1, 2, 3, 4, 5, 6, that's a 0, and same thing with this. Now if you choose this one gets a little bit, the one on the left, you end up getting a little different charge here. So in this specific case, carbon has 1, 2, 3, 4. It has a 0 charge, minus 4, which is 0. Oxygen here has 1, 2, 3, 4, 5, but it's coming in with 6. So 6 minus 5 gives you positive 1. So that definitely would not work. And then here is 6 and 7. So it's going to be 6 electrons that oxygen is coming in, minus 7. That gives you a negative 1. So in this specific case, you want to get the overall charge of 0. However, you also want to make sure that those elements end up getting it. So the answer here would be definitely the second one. Okay, let's move on to VSEPR real quick. So VSEPR model is an example of what happens with geometry with Lewis dot structures. So if I take a look at VSEPR as an example, we always start talking about two things. The first one we're talking about is, what does it stand for? So VSEPR stands for valence shell electron pair repulsion. Now it's a mouthful, but basically what it means is that electrons in the valence shell are going to have repulsion forces. They're going to want to be as far away as possible from each other. And usually that structure is going to be given an atom, and it's determined by minimizing that repulsion. And so let's talk a little bit about what that means. If you're talking about a VSEPR model, what you're really talking about is drawing the Lewis dot structure first. Second thing is you're going to count how many electron pairs you have in such a way that you minimize that repulsion. Number 3, you're going to determine the positions of the atoms when the way the electron pairs are shared. And number 4, then you're going to figure out the molecular structure from the position of the atoms. And so there's usually a name that kind of gets attached because of VSEPR. So let's talk a little bit about VSEPR in terms of these shapes. So go ahead and see if you can create a shape for these by looking at that worksheet that I gave you online. And that one actually has a good description of what it looks like when you're talking about pH3, CF, SF4. Okay, so pause the video and see what happens. Okay, so if we take a look at HCN, HCN is going to be a linear molecule. Now the H and the C are going to be a single bond. You're going to have a triple bond with the nitrogen. In this specific case, you have a 90-degree angle because you're not really dealing with a lot of repulsion in that case. So this is actually a 2 carbon in the middle, nitrogen hydrogens on the side with a linear form. For pH3, it's going to be trigonal pyramid. And that one's going to be a 109.5 for approximately like a 107 degrees. And it's phosphorus in the center with the NH3s across. You do get some repulsion because of the phosphorus in the middle. So that one kind of bends the angle a little bit. And SF4 is going to be the seesaw, or we call it a 90-degree angle. And so if you take a look at our exceptions to the rule, it's going to be 4 up there. And so sulfur comes in with those electrons. You're going to get the 90-degree and the 120. Okay, now refer to that list to kind of get the geometries for that part. All right, O3. Let's see, just pause that video if you want to try it out for O3. Okay, O3 is going to be a little different. This is going to be a bent shape, and so what you're going to end up having is a 120 degree. And then KRF4 is going to be, in this case, a square planar with a 90-degree angles and a 180. So you should be able to see those in the chart as well. Alright, so the question here for today is, if a molecule that has polar bonds will always be polar, if true, explain why, if false, provide a counterexample. So a molecule that has polar bonds will always be polar, and the answer here is it's false. And giving you an example of counter ones is that there's going to be situations where you're going to have polar and non-polar parts of that molecule, and sometimes what's going to happen is that it's not going to be completely polar. And alcohol or ethanol is a great example. Isopropyl alcohol is you have OH groups, and sometimes you're going to have CH4 groups. In those specific cases, you're going to end up getting two parts of that, probably a nonpolar region and a polar region. All right, so let's talk about the CO2 and drawing this out. So draw the little structure for CO2, and the question is, does CO2 contain polar bonds? And is the molecule polar or nonpolar overall? And so normally what you'll find is CO2 for the most part does contain a little bit of polarity, but if you take a look at the dipole moments for this one, it actually cancels each other out. And the question is, the molecule overall is considered to be nonpolar, but it does have some properties when it goes and dissolves in water. And so CO2 actually has a little bit of polarity in there because of the oxygen groups. And so if you take a look at CO2, usually you'll find it in soda. Okay, so another question here is, do lone pairs make a molecule polar? If true, explain why. If false, provide a counterexample. And the answer is it's usually false. Lone pairs don't really attract that. And what you'll find is specific cases where if you actually have a lone pair in, it doesn't have the same properties as pulling those electrons when you have something like water, where it has that highly electronegativity on there. All right, so let's skip over to the next part, which is the VSEPR theory, and specifically thinking about the different examples. Now earlier I did talk about how to do these shapes. So first off, what you want to do is take a look at how many lone pairs you have and exactly which ones are getting shared. So as an example, if something is linear, you're going to have number of electron pairs, you're going to have 2 electron pairs. So usually you're going to be flanking the middle atom, in this case carbon. So you have 2 pairs of electrons, one on this side and one on this side. So pretty straightforward. The best example is going to be like carbon dioxide. Now if you take a look at something like trigonal planar, in this specific case you have 3. And trigonal means from 3, it's plane because it's only on one side. And in this specific case you're going to get, let's just say we have your 3 areas around, and they all spread in about 120-degree angle. And so there's a couple examples of this that you'll see later on in your book. Now a tetrahedral is a very classic example of something that has 4. So the word tetra meaning 4, and then hedral meaning it's a 3-dimensional shape. And CH4 is a great example of a tetrahedral example. What you'll find is that it forms like this, almost kind of like a pyramid. It's a little different from the trigonal planar because instead of having 3, you have 4 attachments. Trigonal bipyramidal is one where you actually have 5 attachments. So 1, 2, 3, 4, 5, or 5 bonds, and you have a 90-degree and a 120. So 90-degree between the 2 parts right here and the 120 across. And then octahedral is when you have 6, and then you basically have 90-degree angles across. So structures can actually have 4 electron pairs around them. So usually if I give you the example of a tetrahedral have 4 things, you can actually have 4 different types of molecular structures. And so when we're talking about electron pairs, yes, you have your tetrahedral shape, your CH4, but you can also have a trigonal pyramid or a V shape. And the reason why is because you actually have 4 attachments, but instead these lone pairs is what's creating the repulsion. So the lone pairs, for example, in a trigonal pyramid, is that you have 4 attachments, but that lone pair tends to kind of push it down. And so when we actually draw it out, we don't actually put down the lone pair here, but we indicate that there's actually a bent piece. Same thing with the V shapes. Here's other examples where you get 5 electron pairs around the central atom, but you have 4 different structures. And so in this specific case, you're talking about trigonal bipyramidal. You have a seesaw, which I talked about earlier. The T-shape, which you have 2 lone pairs, and notice carefully, lone pairs tend to kind of push everything aside. And then you have your linear, which is when you get 2, but then you have 3 lone pairs around here. So it kind of gets a little bit crazy when you start getting these electrons as lone pairs because they tend to push everything to the side. Alright guys, well that was about it. So make sure you practice your Lewis dot structures, and also make sure that you understand the different types of structures based off of how many attachments you have.